Swayam Prabha. Digital India. Educated India.
So, we are looking at longitudinal perturbed motion of an airplane about an equilibrium flying condition, which is this is a cruise condition, and we have already derived the perturbed equations of motion. This we have written yesterday also, only for the sake of completeness I am writing this again. And we call this matrix as A long, and this is the vector of the longitudinal perturbed variables. okay. And we said that if you want to look at the free motion of the aircraft with respect to the perturbed variables around this equilibrium flight condition, then actually we are solving an eigenvalue problem, right. So, we are solving this, right, and this gives me a quadratic equation in lambda. So, we will get 4 eigenvalues. This quadratic equation in lambda results in 2 pairs of complex conjugate eigenvalues for this particular matrix, okay. So, not that it will always happen, right, 4 eigenvalues can be in different combinations. So, here what happens is, now for this particular matrix, in the flying condition that I am taking, we get 2 pairs of complex conjugate eigenvalues, and they are actually well separated in the complex plane, okay. Lambda 1 and 2 are corresponding to the Phugoid motion, and lambda 3 and 4 are corresponding to the short period motion, okay. Because of this separation of the eigenvalues in the complex plane, they are quite far located with respect to each other. We could make some assumptions to simplify this equation further, right. Solving a quadratic is actually a difficult task, it is not an easy task if you want to do it by hand, right. So, what you can do is you can use this fact that the eigenvalues are well separated in the complex plane and make some assumptions, so that you can arrive at an expression for the short period frequency and the damping and the characteristic of the Phugoid motion, right. So, what we did yesterday, we assumed the short period mode to be a pure pitching motion. So, we looked at pure pitching motion of aircraft about this flight condition, right. So, if you are doing a wind tunnel experiments and want to measure the frequency and damping corresponding to this pitching motion, then place your model in the wind tunnel so that you are satisfying this equilibrium condition. So, this x axis of the aircraft is actually aligned with the airflow. And this model is having only one degree of freedom, and that is in the pitching motion. It cannot, so there is a rod going passing through this, which allows it only to have a pitching motion and nothing else, right. And we assume that to start with, this axis is aligned with the inertial frame of reference, so that any perturbation from that delta theta was equal to delta alpha, right, and delta theta dot, which is delta q, we have shown this already. Yeah, right. Delta theta will be equal to delta q even if it's not aligned, x is not aligned with the x axis of the inertial frame of reference. So, we derived that we arrived at the equation of motion for this pure pitching motion, and that was now we are looking at the motion with respect to disturbance coming from the disturbance in the wind, not because we are giving an input to create a disturbance, right. So, we will look at the response in alpha with respect to the disturbance which is coming from the wind and not because of the control input, right. Delta E is the perturbation in elevator, right. So, if you want to look at the free response of aircraft, then you drop this 0 and the homogeneous part of the solution is this. Okay. So, what we have assumed here is that the response general form of the solution is something like this, and then we have solved an eigenvalue problem which is this, right. So, corresponding to this motion, I can find out what frequency and damping ratio are, right. How will the response look like? So, clearly the response is consisting of two parts, right. One is the amplitude, which is governed by this part, right, that is also a function of time, right, and this sinusoidal part. So, it is going to be oscillatory and the amplitude should be damping in time, because amplitude is being governed by this particular term, is not it. So, here I am assuming that the real part of the eigenvalue is negative, right, the way I have put it here. So, when t is increasing, this part is going to decrease, and that is how the amplitude will go on decaying. Yeah. Okay, let us look at this first. Okay. Many of these things you can learn in many other subjects, right, mathematics, vibrations, but let us try to understand the flight mechanics or dynamics part. Okay. So, mathematics you can learn in many other courses, right. So, this is governing the amplitude and this is the oscillatory part. So, if you want to plot the response, which is the perturbation time response of the perturbation delta alpha, or time response of the perturbed variable delta alpha. Okay. So, I should not say that as perturbation. So, you actually have a perturbation which is delta alpha at time t equal to 0, which is this, right, and the response can look something like this. Okay, not there is only a qualitative picture. So, what is happening? The amplitude is decaying, right, only because I have taken this part to be negative, right. Otherwise, it is going to, if this part is positive, then the amplitude is going to grow in time. And this picture is correct with respect to our assumption that short period mode eigenvalues are lying in the left half complex plane, right. So, this is going to be a negative term. Okay. So, this is what the response would look like. Okay. So, this is the damped time period, And there are other parameters also which normally we talk about when we talk about second order system response, and those parameters would be time to double or half. Okay. And that is given by or the real part of the eigenvalue. So because I have because I am looking at the oscillatory response, or not saying is decaying or growing, we can call this as another parameter is number of cycles that it will take in the time to half or double the amplitude. Okay. This is roughly equal to 0.11 or okay. So we keep this here for a while. Okay. Right now we are just looking at simpler motions. Okay. So this was for pure pitching motion, and we arrived at the expression for frequency and the damping. Now let us look at Phugoid motion. Phugoid, we said that it is an exchange of energy. So you get a change in forward speed coming from somewhere, and then the aircraft will start going up, okay, lose that extra energy and gain a height. So when you gain the height, you have actually gained extra energy compared to your equilibrium flying condition. So we want to so you have to remember this. You are, when you are flying, you are sitting here, right, and now there is a perturbation, and we are trying to find out if the system is stable in that particular equilibrium flying condition or not, or your airplane, right. So we have to see if the ball is eventually back to this equilibrium condition or not, right, and then only we will say that the ball is stable in this equilibrium condition. So similarly, if you think of this Phugoid motion, what I was saying is you are flying along this line, constant altitude, it is a level cruise condition, and then there is an increase in forward speed. So delta u naught is the equilibrium speed, and add that to this delta u. So because of that, there is a increase in kinetic energy, and the only way you can exhaust, or the aircraft can exhaust this energy, is by gaining some height, right. So it's gaining some height, and now there is an increase in the potential energy, right. So eventually it should settle down to this if the aircraft is stable in Phugoid, isn't it? So we assumed that there is no change in angle of attack in this motion. So delta alpha is 0. There is a change in forward speed, and the flight path angle will change, then only you will get this height, right. You will attain this height because of the disturbance. So there is no pitching motion involved here, it's only change in the attitude. So earlier models, the first one which Lanchester gave, was based on this physical understanding. Okay. So he said that energy is conserved. So whatever energy you have, that's conserved. Okay, let me just try it. So finally, when the disturbance is being killed, you are actually trying to come down to the initial energy level, right, which was, no, you have a forward speed. So kinetic energy at the equilibrium condition is half m u naught squared, right, and it will be flying at some height. Right. So if there is an increase in the kinetic energy, that is being compensated by or decrease in potential energy, right. So, that is what this expression means. So, balancing these two, you can find out this expression by assuming that these perturbations are small. So, I am dropping delta u squared term. Now, let us look at the equation of motion in the normal direction. Okay. Right. So, I am writing down the equation of motion for this case in the normal direction. Right. So, this acceleration is because of imbalance of force in the vertical direction. Let us also try to linearize this. Okay. Now, because there is no change in angle of attack, I can so there will not be any change in the CL, right. So, this CL value is the CL at the equilibrium flight condition. Is this all right? Now, if you assume this theta naught also to be 0, which is my flying condition, then this is 1 and this angle is small. So, this becomes 1, sin theta naught is 0. So, what you have is this into 1. Now, there are two components. If you expand this and then drop delta u squared because the perturbation is small, then what you can get by doing this is the perturbed motion in the vertical direction So, you have an equation now in delta z, right. This comes from lift equal to 8, which is true in this flying condition. So, finally, what you get is an expression for frequency from here, right, because a second order equation with no damping. So, you can find an expression for the frequency of this motion, right. So, then there is an assumption involved here, right, and that is there is no change in angle of attack, there is no pitching motion involved in this, but what we have neglected here is the damping. Somehow it has got neglected because of the assumptions that we have followed. So, Lanchester could only arrive at an expression for the frequency of the Phugoid motion, and he could not give any expression for the damping, and therefore, he could not comment on the stability of this motion. Okay, so, if you want to look at the stability or dynamic stability of the motion, right, around the equilibrium flying condition, then you have to solve an eigenvalue problem, right. So, if I now use some of these physical assumptions and try to look at how we can simplify our linearized equations of motion, then we can probably be able to find out expression for frequency and damping both. So, let us look at now the Phugoid motion using this set of equation, okay, and use the assumption that people followed. So, assumption here is that delta alpha is 0, which also means delta W is 0. So, delta W dot is 0, delta Q dot is 0. So, try to extract a simpler model from this. So, first equation is now with this assumption and this will be this equation is not going to give you anything. So, delta Q dot is 0, delta Q is 0, delta W is 0, and the fourth one gives you so this I use to arrive at this, okay. From this equation you can find out what is delta Q in terms of delta U, right. So, the model that you have is this. And solve an eigenvalue problem now. So, you will arrive at the frequency of the Phugoid mode, which is interestingly the same as what Lanchester obtained. Frequency is the same, okay, what we achieved by doing this analysis. And the damping ratio turns out to be and XU is this. No, this we have derived if we assume CDU to be 0, which is all right, you know, so good assumption. If we assume that we are not accounting for the compressibility effect. So, the damping in Phugoid is so again I am using L equal to W equal to mj in this. So, what you see is the damping in Phugoid is inversely proportional to L over D. What is L over D? Lift over drag, right? Which is called aerodynamic efficiency of the aircraft, right. So, what it means is that if you have L by D ratio which is high, the damping in Phugoid is low, right, and Phugoid is a slow motion. You may be able to control it, okay, because the time period involved is large. So, you have enough time to act, but let us say you are very close to the ground, this kind of motion is going to take the aircraft up and then hit the ground, right. If it is very close to the ground, it can give you a bumpy ride, like hitting the wheel on the ground and so on, right. The frequency is inversely proportional to the trim speed, right. So, let us say you would still want to keep this L by D high. So, what we get is this zeta or P, damping ratio in Phugoid, goes down, and let us say it is not meeting the requirement, okay. So, there will be some requirement on these parameters, like how much value there should be. If it is not meeting that, then you have to go for control systems, right. So, in the next class we will look at Phugoid short period approximation.